We mentioned talking about accretion disks, and so here we imagine having a black hole, and we have gas that flows inward for various reasons. For example, a merger between galaxies or a binary star pulling gas off of one star and forming an accretion disk around the other. And so we imagine a sort of flat structure that forms, and here is a disk-like structure. So here is gas rotating around the black hole. Here's gas further in. We make an assumption that the orbits are circular and flat, and there are some theoretical reasons why we think this is a decent approximation. So if we think of the solar system, right, we think of a planet further away, it has some angular momentum and it has some energy, and then we think of a planet further in, it has also angular momentum and energy, but they are less. So in going from further out to further in, both energy and angular momentum decrease. And the idea in this picture is that as the gas moves inward for some reason, right, there's a loss of angular momentum, so there must be a torque. That loss of angular momentum is accompanied by a loss of energy, and that energy gets radiated away, and we see the disk. So these are bright structures as a result of this. And so we sort of want to think of angular momentum and energy not for individual planet-like objects, but for a disk, or what we call an accretion disk, right? So accretion is the thing that allows angular momentum to be angular momentum and energy to be extracted. So we call this an accretion disk. And so we think we can construct the equations for the accretion disk by thinking of a continuous distribution of matter, and so annuli at different values of r. So that's the radius from the black hole. And so we can imagine having right there. So there's an amount of mass in each annulus. An infinitesimal amount of mass, dm, it's a flat two-dimensional structure, so we have some density, right, sigma, some surface density, and then we have to multiply that by an area. That area is the area of this infinitely thin ring, and so the radius is 2 pi r, sorry, not the radius, the circumference, right, so we have a little tiny annulus, which we can open up, right, pull apart, open it up, and so it has length times height, so that's 2 pi r, and that's dr for the height. So we have an amount of mass, dm, in there given by this expression, and therefore we have an amount of angular momentum, dl, there, which is the amount of mass, right, mvr. So mass times v, and this is call it phi, subscript phi, because it's an angular velocity, and then we have r. Right, we're imagining perfectly circular orbits. We have sine of 90, so it's dm v phi r, which then translates to sigma function of r, 2 pi r dr v phi times r. So we can think of the distribution of angular momentum as a function of r, or the rate of change of angular momentum in r, as given by the density, 2 pi, we have an r squared times v phi, and what's the v phi? Well, we're circular orbits, we have m v phi squared, right? That's ma for circular orbits, and that's equal to the gravitational force due to the black hole. So Newton's universal law of gravitation. And so we'll get V phi as, so here we get sigma of r 2 pi r squared times, we get the square root of g mass of the black hole over the square root of r. And so we can then write this as 2 pi, let's pull the constants out, g m black hole to the 1/2 sigma of r to the 3/2. And if we want to know the distribution of angular momentum in this disk, right, L as a function of r, we have to integrate this. So we get 2 pi constants. We integrate from some inner value of r to some outer value. We integrate the density times r to the 3/2. Let's say that the density is everywhere the same. Say sigma of r is equal to some constant c, or let's make it sigma naught, some constant. Then the angular momentum as a function of r becomes, or we pull this out of the integral, we get 2 pi g mass of the black hole to the 1/2 sigma naught r to the 3/2. Then we look at the angular momentum in the disk as a function of radius. Right, that looks like an r to the 1.5. So as we'll see, that these disks terminate at some inner value. So let's put r star, whether we want to evaluate from there or not, depends on what we put here. But the angular momentum like this would be something like that. Right? So the angular momentum is decreasing as a function of r. There must be some, again, torque that's responsible for this. So maybe next we'll look a little bit at the concept of torque and get a sense of what that looks like.